Greetings. I would like to make a short video about confidence interval estimation. Uh, Remember, we did this in class yesterday, and I want to make a short video that can summarize the methods I mentioned yesterday. And after I do this summary, then I'm going to show you how to test a hypothesis for one mean. So I have prepared a few notes to share with you, and I'm going to start those notes now. So bear with me because live production has its problems. I'm sharing the screen. So for confidence interval estimation, we have some methods that come from older times. Stupid thing wanted to do this now. So unlike other people, I'm not going to show you immediately commands. I'm going to show you the methods, and I'm also going to tell you when these methods are applicable. Most people will show you commands, but just commands don't really make what you calculate correct or valid. Only when the mathematical requirements are met, then a method is valid. So to do a confidence interval estimation of the mean of a continuous random variable, so a continuous random variable is a random variable which is numerical, and the range is taken, the range of the values is a continuous range, it's not discrete, it's not like the values 1, 2, 3, 4. They're discrete, they're continuous, like for example, height or weight or temperature. Those are typical examples of continuous random variables. Now you have one in your mind, and which I call x, and you want to estimate the mean of x. Okay, so here is the mean of x in Greek. Now, the classical method tells us that you have to use the t-statistic, and here I have the t-statistic. So you take the sample average, the t-statistic is defined in the following way. You take the sample average, you subtract the value that you don't know and you want to estimate, and you divide by the quotient of the standard deviation divided by the square root of the sample size. This is the sample standard deviation, the S, so you know it. This is the t-statistic. Now, you can always calculate the t-statistic, but what nobody tells you is that the confidence interval estimation, what you mean confidence 95 or 90% or 99%, comes after a certain requirement, comes after knowing the distribution, which is the probability model of the statistic T. That particular type of distribution is called sampling distribution, because this is a probability model. It reflects the sampling distribution, reflects a probability model that comes from the way we collect the samples. That's what it's called, sampling distribution. Without knowing the sampling distribution, you cannot guarantee any type of confidence for your confidence interval. So your work will have no validity at all. Now, to have this sampling distribution calculated, to make the mathematics work actually, you need one assumption, that X, the random variable which you study, from which you collected the observations, must have normal distribution. Well, no random variable will have precisely normal distribution when you judge the random variable from the data. So always we mean that this should be taken with a sufficient grain of salt. That's why we say that in practice, X must have approximately normal distribution. And I will show you an example of what I mean later on. Actually, today I'm going to show you pathological examples. When X has normal distribution, then the statistic T, which you will use for the estimation, has students distribution. This is a very old theorem. It goes back to the beginnings of the 20th century. And then you have this particular confidence interval. This is going to be your 1 minus A minus alpha confidence interval. This alpha is the Greek letter alpha. It's like the American, the English A, not different. Takes values which are 0.01, 0.05, and 0.1 typically. Most typically we use 0.05, and then you will have the 95% confidence interval. Well, we will do this, we will complete this later on with R, but most of times the data don't come from a normal distribution. So the question is what you do next if the data don't come from a normal distribution. Then you can use a variation, actually a corollary of the central limit theorem, which works only if you have a big sample. Now, how big is big? This is a matter of interpretation. But there are some rule of thumb, some rules made by the experience of working with examples. If your distribution is not very skewed, or if the data don't have a histogram which is very skewed, 40 or 50 will do well. It's a big sample, so you can apply that technique. You also need, 40 or 50. So in this case, that theorem, which is a variant of the central limit theorem, tells you that the statistic T that I showed you before does not have student distribution, but has approximately standard normal distribution. Now, when your sample size is greater than 50, the differences between the student distribution and the normal distribution are really not very visible. And this is going to be your confidence interval. So this guy here, you find by using the quantile command for R, okay? So for example, if I want to find alpha over 2 for alpha equal 0.05, and then I take the quantile function, Q, because I use the normal distribution, the standard normal, I use the command Qn, and I will put here 0.025, and this, then the value I will read is approximately negative 1.96. This is because you're looking at this part of the distribution. So this area here is 0.025. And because this is on the left, because it has small probability under the curve, small area under the curve, this number has to be negative because the center of the standard normal is 0. That's why you get this negative 1.96. And of course, you throw the negative sign on and you just keep the 1.96. So that will be 1.96 and here in both cases. Now, if the data are 50 or 40, that can be a decent estimate, but may not be the best estimate. So in these cases, when you have to break away from the assumptions, from that accurate assumption, apart from this, I would recommend also the bootstrapping method to be used to calculate the confidence interval, and I'm going to show you right away the bootstrapping method. One more thing, it doesn't matter if you do more than one method to calculate your confidence interval. Statistics is not calculus. So you better use all the available methods you have and you can use are valid to use for the particular calculation. So here, let's summarize before we go to R to show you some R commands. Not that I'm, super duper R guy, no. If you can verify with a Shapiro-Wilk test, this is the test that can verify that you have normal distribution. I will show you how to use later. The data come from normal distribution, so that means the underlying random variable is normally distributed. Then you have one accurate method, and that's the T. Use the T statistic, and this is your confidence interval. If not, then you have to go to contingency plan. One is if you have a big sample size. If you have a big sample size, then you will use the variant of the central limit theorem. This is your confidence interval, but I also tell you to do the bootstrapping. Now, if you don't have that requirement, if your sample is still small, then and you don't have normal distribution, you cannot ascertain that, then bootstrapping. That's your only available methods. In the past, we used to transform the data. For example, take the logarithm or take the square root of the data. So those were looking like ln of x. So if the data were very skewed and positive, something like this, then they would try to take the logarithm of the data in an effort to make them a little bit more, to cut the skewness here and create a little bit of a left tail and say that now the data are approximately normally distributed and use the T. I don't like these methods because they have one problem. You want to find the mean of x, okay? What is the mean of x? It is the expected value of x. This is what you want to estimate. Well, if you drop x and you work with the logarithm of x, the expected value of the logarithm of x is not equal to the logarithm of the expected value, because simply the logarithm is not a linear function. So you will be estimating this and you will have no idea about this. And you can't say, oh yeah, the data have this mean, this confidence interval. Now will take, because this is for the logarithm of the data, now I will take the exponentiation and I have the confidence interval for the mean of x. No, that is not going to work simply because of this technique, of this particular inequality. So if you really want to work with the with the original random variable, you can work with the bootstrapping method. Of course, you can take a nonlinear transformation of the data, as we call this, and apply the previous techniques or even bootstrapping for this. But if you can apply bootstrapping, you just go with the original data and be done with it. Those methods are invented because we had to have ways to go away from this particular ideal case. So mathematics want to work to devise tools to work with the non-nice world, the exceptions of the rule. This method, the nonlinear transformations, could be used and have been used many times effectively and with good results, but they can only give us qualitative, not exact quantitative statements for X. They can tell you for this, but not for that one. Okay, and with this now, I want to go back to change that window. So I'm going to stop sharing here. And now share a different window. Now let's find where the share is. Here's the share. Window, we want R Studio. So now you see my R Studio here. And I worked with a data set, which is here, growth dipterics. I'm going to show you the data. You have 41 data points. And this is, let me tell you the story. I took this from the book I use, which is the introduction, the statistics for biology, analysis of biological data. I started using now the third edition of this. It's a very nice textbook because it doesn't engulf the students with many math details. I think it has slightly less than what I want, but it has one good aspect. It puts the student to work with the data. That's why I use it for many years. So here there is that kind of, it's a kind of planetary, something like this in a tropical environment, and it's called dipteric something. And they did of the growth rates by basically looking at the trunk of the tree. And then because the data were obviously very skewed, they took the scientists decided to take the logarithm of this data. So here is, those are 41 measurements of the logarithms of the growth rates of this dipteryx plant in some region, I think from Brazil or something. Anyway, now suppose I want to find the average of the growth, of the logarithm of the growth rate. Logarithm of the growth rate. Don't forget that. That's my random variable. Obviously, it's a continuous random variable, and I want to see if it is normally distributed. So first, I'm going to do. I mean, you have R, so you can do many things. Okay, let's look at the histogram first. And when you look at the histogram, too bad. You see here, you have skewness and entire lack of symmetry. This histogram is telling you that these data do not come from a normally distributed random variable. So there's no way we can apply the t to use the t statistic to calculate the confidence interval with sampling distribution, the student distribution. We cannot apply what we said before. The exact method for the calculation is not applicable simply because the data don't come from a normal distribution. I also advise you to do, not just look for the histogram may look okay at some point, or you may do the box plot. And here, if you do the box plot, diabolically, the box plot is very deceptive. Look at the box plot. You would say, yeah, there's a small variation from normality. Look, almost symmetry. Just one whisker smaller than the other. Not too bad. Unfortunately, the truth is that it is too bad. So bad that if I do the Shapiro-Wilk test, which is this command, the Shapiro-Wilk test gives me p-value 0.001, very small. Okay, how are you going to use, how you use the Shapiro-Wilk normality test? Typically, your guidance comes from the p-value. So the smaller the p-value, the further away you are from normality. I wouldn't take a random variable to be normally distributed if I don't see a p-value here equal to 0.6 or more. If I see 0.4 or more, I would say, yeah, I don't have normality here. Normality is very questionable. So what I would do in this case, I might have reported, not of course with so small p-value, but let's say that my p-value was 40%. I would have reported the t, the confidence interval I calculate by using t with the student sampling distribution, the exact calculation. And then I would have done also the bootstrapping, saying that the claiming I'm doing the bootstrapping because the Shapiro-Wilk test is not erring on the side of normality with vengeance. But here, the case is very different, so you can't do that. So you have to use the bootstrap commands, and the bootstrap commands, if I look at my history here, look the following. So I create the boot min. So what is the before I show you this, let me share a few things about bootstrapping. I'm just going to introduce bootstrapping very briefly. So let me stop the sharing from here and go back to my tablet, and I got to share from here, my notability. So now you see this. Sorry, bad call. What is bootstrapping? So you have the data from X. You have n data points. You collected n data points. Well, those data points have a distribution which is called empirical distribution. And basically, this is the probability model that comes from the observations. And for now, I'm going to call it, I'm going to give it a name F. And I will put a tilde and I will put a subscript n because I have n data points. The random variable x also has a distribution function. This is what we call the cumulative distribution function. So when I use the word distribution function, means cumulative distribution function. And I will call it f sub x, okay? There is a theorem that tells me that as n tends to plus infinity, the empirical distribution tends to this, approximate. In some sense, I'm not going to tell you the exact sense right now because that's really deep math. But in practice, you will see this is expressed by here, this is expressed by the step side graph. So these steps occur when you have a value in the data points. And basically the difference between each step tells you the frequency in which those, the relative frequency actually of the actual x sub I plus 1 value. The value, its numerical value has a certain frequency in which it appears, with which it appears in the data set. That gap here is expressed by this. And and another thing associated with this is the histogram, okay? So that's the graph of this, and the graph of this would be something like this, okay? It's always going up, let's say. I'm not very good with, graphing. So the more data you have, these steps will start coming closer to one another and start approximating this. And these gaps will become smaller because the more data you have, the values start coming closer to one another. That's the nature of this theorem. So bootstrapping says, I have no way to know f sub x. I don't know what is the probability model of x, but I have to work with the data. So assuming that the empirical distribution, the information, the probability information about x that I have from the data is good enough. What does good enough means? Sort of close to the unknown distribution of the random variable. Then I forget f sub x and I say that all possible values I pretend, that's what I mean, I say, all possible values of x are the values I have collected. That's the trick. So now you use a simulation, which is called Monte Carlo, and I'm not going to explain why we call it Monte Carlo now, to create many random samples from the data that you have collected. So what you do, resample the data. So you collect samples of sample size n, same as the sample size of the original data, but with replacement. Why with replacement? Because each time, what is the way we collect a random sample from a random variable? We make n independent observations. How can you make n independent observations when you have only n possible values? You sample from these values with replacement. So this technique is done by bootstrapping. And then bootstrapping, if you want to calculate the mean of x, that's your objective, the bootstrapping will calculate the means of the samples. So it will take the sample averages. Let me give them a different notation now. It will create the means of the sample average of the sample I, and this I will go from 1 up to 10,000 you can do. Here in my example, I have done 1,000. Then I will calculate my confidence interval using this. That's a little bit reminiscent of the central limit theorem. Why? Because the central limit tells me that if you take all the possible samples that you can generate from the random variable, you go and collect data. You don't do anything else in your life. You just collect data from X. Then these will be, because they're averages, they form on their own a new random variable which is called sample average. When you have one data set, you collect one value. If you create many data sets, you collect many values of this. This is a random variable, so you see what we call its realizations, observations of that random variable. And what is said by the central limit theorem, this is approximately normally distributed. So you will see that I'm imitating this process here, but I cannot get everything out of X because I have only these limited observations. That actually creates a limit into the validity of the central of this process of the bootstrapping, and that limitation depends on how representative of the variability of the random variable X are the data you have collected. Okay, now I can go back after to my R and stop the setting here. And now we share our R window for the last step. So let's go back to our window. So here I'm going to create a function. Obviously, I don't know what that function means. It means that I create with an iterative process what is called the boot mean, which is the mean that comes from the data. You remember those means mu of the sample I? That's exactly what this thing is going to be. And I'm sending this to console. Worked fine. And now I'm ready to do the bootstrapping. This is telling you how what the calculation is going to be for each sample. The samples will be generated by this command. And my samples were, I need to, okay, I'm sending it to the console, but I have to give the correct, this is growth. I had used that command from another data set. So I'm putting now the correct data set here. Mistake. Load the package boot before. You need to load the library. Now let's run the commands. We didn't need to run that anyway, because we had already defined it. We just need the boot. And now we have this. In the boot, oh, sorry, environment. I need the environment. Here are you see, here are the boot results. They come in the form of a data frame. And you're interested in this. I did 1,000 observations, and those averages for each of the 1,000 samples I have generated with this random process are collected here, are basically in this particular variable. So if I want to see them now, I want to do hist to do the histogram, and you will see how better they look. Select the boot results. Now put the dollar and T, okay? Because these are the T data. T0 is the original, the average of the original data set. And here you have the histogram. It does have some lack of symmetry, but it's a lot better. Now, what we do is that we will do the so-called parametric bootstrap interval estimation. So we look here, and the height of each one of these rectangles represents relative frequency. Basically, it's frequency divided by the total number of the samples. I have 1,000. So if you divide these numbers by 1,000, you will see the relative frequency. I want to cut area under the those jaggy lines of the histogram, which is equal to 0.025 on the left and 0.025 on the right. And if you do this, then you will get the so-called percentile confidence interval. You can do this automatically with this command. I'm sending it to the console. And here you see the command. So that's your confidence interval. Now, I had 41 data points, so I could have calculated already I could have applied the variation of the central limit theorem, because the sample was not very big, was not small either, was in this iffy territory. How would that look like? Okay, you need t sub 0 here, which we calculated. That was the t sub 0. The t sub 0 that you show here is actually the X bar of the data. So it's 1.31 minus, now you have to put a multiplier. I told you that because you use the standard normal for 95% confidence interval, this was 1.96. And now you have the standard deviation times SD of the data divided by the square root of how many points you have? 41. So that's the left end. You see, it's very close to that one, but this one seems to be a little bit better. I'm also going to do the previous command, that command, but now I'm going to change this negative sign to a plus to find the right end of the interval. You see 1.61. So even that one was not that bad. Okay, so you have two different intervals. Now, which one are you going to take? Honestly, I would take the union of those. I would report both, but my mind would go that anywhere between 0.976 and 1.61 is the mean of the logarithm of the growth rate, the annual growth rate, that what was this, of these dipterics plants. So I am going to stop here. Thank you very much for watching.